Now let's think about whether we could pick up these neutrinos on Earth. Let's imagine the nearest recent supernova, 1987A, was in the Large Magellanic Clouds, which are about 50 kiloparsecs from the Earth. So let's have the Earth down here. How many neutrinos will have reached us? So once again, we've got 10 to the 57 neutrinos coming out. And they're now going to be spread over a sphere of radius 50 kiloparsecs. Kiloparsec is 1,000 parsecs, so that's 50 times 1,000 times a parsec, which is about 3.1 by 10 to the 16 meters. So that comes out as about 1.6 by 10 to the 21 meters. So, how many neutrinos do you get per square meter at the Earth from the supernova explosion? Well, you can simply take the 10 to the 57 and spread that uniformly over the sphere. So divided by the area of the sphere, which once again is 4 pi r squared. We've got r, so that comes out as approximately 3 by 10 to the 13 neutrinos per square meter. So that's 30 trillion neutrinos went through every given square meter of the Earth when the supernova went off. 30 trillion neutrinos. You know, 1 square meter, that's about the area of a human body. 30 trillion neutrinos went through your body, if you were alive in 1987, for every body on Earth at this time. I mean, wow, that's a lot of neutrinos. Why weren't we all fried or murdered or something like that? Well, once again, we have to bear in mind this extraordinarily small cross-sectional area. That is a lot of neutrinos, but would they actually interact with anything? Let's consider a human as a blob of water, as by and large we are water. So let's, for example, take 1 cubic meter of water and fire our flux of water 10 to the 13 neutrinos into it. Would they interact? Well, once again, we've got atoms in here. In this case, it's water molecules. How many water molecules? Well, 1 molecule of H2O has an atomic mass of about 16 for the oxygen, 2 for the 2 hydrogens. That's about 18 times the atomic mass unit, 1.67 by 10 to the minus 27 kilograms. So 1 H2O molecule has a mass of about 3 by 10 to the minus 26 kilograms. So how many atoms are there in a cubic meter of water? Well, that's going to be about the mass of the water divided by the mass of each molecule. Which comes out as about 3 by 10 to the 28 atoms. So a lot of atoms in a cubic meter. But now let's look at our neutrinos coming in. We've got a flux of about 3 by 10 to the 13 neutrinos. What are the odds that these neutrinos will actually hit anything? Well, they've got 3 by 10 to the 28 chances to hit anything. But the chance of a given neutrino hitting a given atom is just the ratio of the total area to the cross-section of that atom. So the area is 1 square meter for a cubic meter of water. The cross-sectional area is 10 to the minus 47. So the probability of 1 neutrino hitting any given 1 atom is 10 to the minus 47. But we've got 3 by 10 to the 13 neutrinos, so it's going to up the chance, so multiply by that. And we've also got 3 by 10 to the 28 atoms. So you factor these all together, you come up with approximately 10 to the minus 5. So we've got this whopping 30 trillion neutrinos going through a cubic meter of water, but on average the odds of even one of these neutrinos interacting with any atom is 10 to the minus 5, 1 in 100,000. What this means is a cubic meter of water is not enough. You need 100,000 cubic meters of water to have a decent chance of even one neutrino anywhere in this huge amount of water interacting with one atom. So yes, there are a staggering number of neutrinos that went through us when the supernova went off, but neutrinos really don't like interacting very much. You'd need 100,000 cubic meters of water, 100,000 tons of water to have even good odds of even one neutrino interacting with one atom. But there is a curious calculation we can do here. What are the odds that anybody actually saw one of these neutrinos? There are a lot of humans on Earth, and humans have eyes, and eyes are mostly made of water. And if a neutrino went into your eyeball, the transparent stuff in there, and interacted with one of the water molecules, it would cause a little flash of light, so-called Cherenkov radiation. Are there enough eyeballs on Earth that anybody would have seen one of these flashes? Well, let's estimate that. How many people are there on Earth? I don't know, about 10 billion. Let's call it 10 to the 10. It's a very rough calculation. And how big is an eye? Let's assume it's a sphere of radius a centimetre. So that's the volume is 4/3 pi centimetre, 0.01 meters cubed. And of course you've got two eyes each. So that would give you the total number of cubic meters of all the people on Earth, which comes out as about 10 to the 5 cubic meters. So, if you had 1 cubic meter, there's a 1 in 10 to the 5 chance of a flash, but there are about 10 to the 5 cubic meters of all the eyeballs of all the people on Earth. So, odds are, one person would have seen a flash from a neutrino.